So consider this sequence. Here we start with 1, and then each time we add the reciprocal of the square of the next number. Okay? So since each time we're adding something to it, clearly this sequence is monotonic. So then the question is it bounded? Well, let's see. If I look at S, let's do S8. That's going to be 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus 1 over 6 squared, 1 over 7 squared, 1 over 8 squared. All right? If we look at each of these, we could say, hey, this sum is smaller than 2 times 1 over 2 squared. And that's because it's 1 over 2 squared plus 1 over 3 squared. And 1 over 3 squared is smaller than 1 over 2 squared. Okay? And we can do the same thing here with these 4 terms. They're going to be less than 4 times 1 over 4 squared. All right? And then I would have this 1 over 8 squared. So what if I did let's do S31. So that's going to be less than 1 plus 2 times 1 over 2 squared plus 4 times 1 over 4 squared plus 8 times 1 over 8 squared. That gets us up to 15. 16 times 1 over 16 squared. That gets us up to 31. All right? So as you can see, Sn will always be less than 1 plus 2 times 1 over 2 squared, 4 times 1 over 4 squared, 8 times 1 over 8 squared, plus all the way up. And that's 1 plus a half plus a fourth plus an eighth. And that's a geometric series, an infinite geometric series. The sum of this series has been known since ancient times to be 2. All right, so the elements of this sequence are monotonic, and they're also bounded by 2. And this has been known for a very, very, very long time. So this implies that this sequence converges. But then the question becomes, what does it converge to? All right? And that's not at all obvious. There's a very, very famous problem called the Basel problem that was solved by Euler in the 18th century. It turns out that this converges to pi squared over 6, which sort of comes out of nowhere, right? So this again indicates the difference between just being able to show that a series converges and being able to find what it converges to.